Once around the Van Allen belts. Discovered by James Van Allen, after whom they're named, these are radiation belts that lap the Earth and bring it in these intense regions of high energy particles. Now, James Van Allen first used a system called rockoons, which is a combination of rocket and balloon. You'd send a high altitude balloon up to clear the majority of the Earth's atmosphere and then launch a rocket from there up into the edge of space. And he got the first hints that there was radiation in space in 1953 with this technique. In 1958, he was able to put a radiation detector onto a proper satellite and send that up. And we had the Explorer 1 and Explorer 3 missions in orbit, spanning from 198 miles to 1800 miles for low Earth and medium Earth orbit altitudes. And then Pioneer 3 went even higher, up to 63,000 miles. That's a goodly fraction of the distance to the moon. That's about a quarter, isn't it? And then with all this radiation, it sort of begs the question, where does it come from? Well, the main source can be the sun, the solar wind, the high energy plasma coming from the sun, carrying a lot of energetic particles, usually charged particles, that can get caught up in the magnetic field of the Earth and create these enormous pockets of trapped particles. Charged particles tend to spiral around magnetic field lines, so the Earth's magnetic field acts as a trap. It gets squeezed on the sunward side and stretched out into a long magneto tail on the downwind side. But another source is cosmic rays, extremely high energy particles from deep space, from across the galaxy and beyond. These hit the Earth's atmosphere and we detect them through the showers of other secondary particles that they tend to release as they collide with the molecules and atoms in the Earth's atmosphere. One of the things that can happen is that neutrons can be ejected as a result of this. So an incoming particle can hit a nucleus and fracture it into a number of components. So for nitrogen and oxygen, for example, can be struck by incoming protons, and you can end up with neutrons, protons, high energy alpha particles, and then smaller fragments like the isotopes of beryllium, beryllium-10, and isotopes of boron and so forth, created high in the atmosphere. And we detect those raining down onto the Earth's surface and pick them up in sediments and so forth. But some of the neutrons are then able to decay into protons and electrons. They are unstable, and the neutrons releasing these electrons and protons can all get trapped, the charged ones, into the magnetic field and create the Van Allen belts. So it's a combination of material from the sun and material from cosmic rays. And there's an interaction between them, which is that when the sun is very active and producing a very strong magnetic flux itself, that tends to protect us from the cosmic rays. And so you do get these, when the sun goes quiet, we get hit by more cosmic rays. It's quite an interesting interplay. So if we look at the two regions, what we find is that there are essentially two belts, an inner belt and an outer belt. And the inner belt is in the region 1,000 to 10,000 kilometers, so 600 to 6,000 miles or thereabouts. And under some conditions, that can close in down onto the Earth, particularly if it's being squeezed by a lot of power coming from the sun, down to about 200 kilometers. So that can be an interesting problem for satellites. And then we have the outer belt, which is further away, 18,000 to 60,000. And there is a very, very sharp distinction, an inner boundary to the outer belt, which we don't fully understand. So there's still work to be done to try and figure out exactly what's going on. But before we talk more about the radiation and what these belts are made of, we have to understand something about particle physics, which is the measure of energy called the electron volt. This is the energy gained by an electron if it accelerates across a field of 1 volt. And because that's a measure of energy, you can also deem it to be a measure of the equivalence in terms of mass. And it's via the Einstein equation, E equals mc squared. So how much is an electron volt? Well, it's not very much, actually. The units will be volts or joules per coulomb, which is energy divided by charge. And so you can actually take voltage times charge and have that be equal to energy, which is, of course, kinetic energy in large measure when these things are moving fast, a half mv squared. The electron's charge, E, is 1.6 times 10 to the minus 19 coulombs. And so if you have a field of 1 volt, you have to multiply by 1 and you get that number of joules of energy. And really, 1.6 times 10 to the minus 19 joules of energy is not very much on human scales. It's going to be need a lot of electron volts before you adds up to anything very significant. However, it does matter to us in all sorts of ways. The energy can be equated to the energy of the different colors of light, and the low end red long wavelength low energy waves in visible light have an energy that's equivalent to about 1 to 2 electron volts. Going up through green, it gets to 2 to 2.5, and then blue and violet, it's in the range 2.5 to 3 electron volts. And this makes an enormous difference to the study of things like photosynthesis and how electrons get a kick from photons of light that can release an electron and cause chemical change, and with a potential difference of about 1 volt, a red photon can do that work and a blue photon can do it twice. But green photons, not much use. They're kind of in between, and they're quite enough to liberate 2, but they're too many to liberate 1 electron from the electron trap inside the magnesium atom in the middle of chlorophyll. And that's why plants absorb red and blue light, but they don't absorb green. They reflect it because it doesn't actually get to work very well. And of course, it's also crucial to us in terms of solar panels and gaining electricity that way. So we now understand a little bit more about an electron volt. We can use that to talk about the energy of the charged particles in the Van Allen belts. The inner belt has a mixture of electrons and protons, and the protons carry very high energies, up to 100 million electron volts. That's really quite a significant amount for a single particle. And these are the ones generally created by cosmic rays hitting the atmosphere. The electrons, they're much lighter, and so they carry energies in the form of 100,000 electron volts. Still a significant amount, but much less by a factor of around 1,000 than that the protons are carrying. And the outer belt, well, that is made mostly of electrons. The protons are not present so much out there. And these are a bit more energetic, going all the way up to 10 million electron volts. So considerably more violent than the inner belt in terms of the electrons. But it's the protons in the inner belt that carry the energy and do the damage. So again, just to compare that, the equivalent of the electron's mass, if you converted it to energy, is 0.511 mega electron volts, so 500,000 electron volts. And that's more than the typical energy in the inner belt for the electrons. But in the outer belt, the electrons out there have enough energy that they exceed the rest mass of an electron, and so they'll actually be able to create matter particles and antimatter particles to go with them, electrons and positrons. And so there's a lot more interesting nuclear chemistry possible in the outer Van Allen belt, and the possibility even of harvesting antimatter particles from it. The protons, well, they are 1,800 times more massive, and so their rest mass energy is getting on for 1,000 million electron volts, 938, and that's more than the inner belt protons carry. So you don't get creation of spontaneous creation of proton-antiproton pairs, just like we do in our particle colliders, who just don't have the energy for that in the inner belt. Now, in terms of its orientation and position, it's controlled by the combination of the sun's and the Earth's magnetic field, and the fact that the Earth's axis is tilted and then the magnetic axis of the Earth is tilted again relative to that creates quite an offset in the plane that would be the plane of symmetry through the middle of the radiation belts. So things are a little bit complicated because of the direction to the sun can alter depending on the season, and so the belts move around a little bit and are offset relative to the pure equator of the Earth. It also means that they are at different heights above the ground in different regions, and this creates something called the South Atlantic anomaly. There is a region over the South Atlantic, over Argentina and the Falkland Islands and Tristan da Cunha in the Atlantic there, marked on the map at the bottom, which sees a weakness in the Earth's magnetic field cause the inner Van Allen belt to be able to come down much closer to the surface of the Earth, to the top of the atmosphere. And this is a dangerous area for satellites. We've lost a number of satellites that have had their electronics crashed or fried completely as a result of going through this region and encountering radiation from the inner Van Allen belt. And so nowadays we either avoid these zones with their orbits or put them in safe mode if they're going to pass through them. So it's definitely something that satellite controllers have to worry about. Now, there is a possible third belt that's been discovered further out in 2013, possibly transient. It may come and go depending on the activity of the sun. So we're not entirely sure about this, but it's certainly out there. And the fact that we're discovering these new things has implications because our electronics, as I've already mentioned in the context of the South Atlantic anomaly, need to be hardened with a lot of shielding to prevent electrical charges being induced in the circuits by the radiation particles. The charged protons and electrons crashing into the circuits can cause all sorts of chaos in terms of corrupting the data or indeed destroying the chips completely. And so we have to shield these things pretty carefully. But if you were to fly through the intense period of bombardment that you would get in the middle of one of the intense regions of the Van Allen belts, you would not want to do that, because even with significant metal shielding, an astronaut would get a lethal dose in about 2 months. So it is something that we have to worry about, and we have to avoid these regions. And in fact, we tend to put satellites in one of 3 places, either low Earth orbit, LEO, between the Earth's atmosphere and the inner Van Allen belt's inner edge, MEO, mid-orbit, between the 2 belts, or GEO, outside both belts. And it is quite fortunate that the Clark belt, the geostationary orbit, where a satellite will take exactly 24 hours to go around the Earth, being 1 day, and thereby match the spin of the Earth, is not inside one of these intense radiation belts. It's a nice, relatively quiet patch of space. And so we are able to put our communication satellites there if it was inside the belt. So if the Earth span more rapidly and you wanted to have a faster, lower orbit, then you might have ended up in the belt, and that would have been a bad result. So we're quite fortunate in that regard. Now, in terms of navigating and avoiding them, not only is it spacecraft that have to avoid it, but astronauts. And when the Apollo spacecraft went to the moon and landed there and came back, or just orbited it, depending on which mission you're talking about, they would have had to navigate the Van Allen belts. And I'm afraid conspiracy theories go that the moon landings would have been impossible because the Van Allen belts would have been fatal for the astronauts. Well, firstly, you'd have to stay inside the Van Allen belts for 2 months to pick up a lethal dose, and these missions only lasted a week, so that isn't right. But in the main, actually, nobody really wanted to pick up a dose of radiation at all, and so they were able to use the geometry of the tilt of the Earth's axis and of the magnetic field as well to plan a route from Earth to avoid the most intense parts of the Van Allen belts and get to the moon without frying the astronauts. There's a combination of the 23.5-degree tilt of the Earth, the further tilt of the magnetic axis of the Earth from that, and the fact that the moon's orbit has another 5-degree tilt compared to the ecliptic plane, all of which can be taken into account, and you can plan your route to go in a looping maneuver from Earth orbit, from low Earth orbit below the inner belt, around the worst of the inner belt where all those high energy protons are, and then as quickly as possible through the thinner regions of the inner belt and the outer belt to try to get away as fast as possible. So you would pick up a dose as you went through there, but you would avoid that intense proton bombardment of the core of the inner belt. And in fact, the Apollo astronauts' radiation dose was less than 5 millisieverts, despite taking, 3 days to go to the moon, spending some time on the moon, and 3 days to come back, and a little trip through the Van Allen belt weaker regions. But most of the time, the radiation was picked up en route to the moon, on the moon, and on the way back, when you are actually outside the protection of Earth's magnetic field. And the moon doesn't really have a protective magnetic field anyway. So most of this dose was picked up on the moon, but it adds up to 1/10,000th of the total that would be fatal. So even with all of that, it's not really a problem. Now, I mentioned that the possibility that you might get antimatter created in the intense parts of the Van Allen belts where the radiation has enough energy. And a satellite called Pamela you have to have a good acronym for these things, was sent up in 2011 and confirmed this. It passed through the lower belt and it discovered that there were in fact antiprotons there, and that the energies in the lower belt ranged all the way up to 750 MeV. So this is really quite substantial, much more than the 100 that was the typical figure for most of the particles, but some of them were really getting quite extreme. And the presence of antiprotons bodes very nicely for the ability to actually harvest this antimatter. And NASA have been putting on the drawing board a mission to go up and try and collect antimatter from the Van Allen belts. Much easier to do this than to make it one particle at a time. in a particle accelerator, which is all we can do at the moment, and makes it by far the most expensive element known to man. Anti-hydrogen, I think, works out around about $1 trillion a gram if you do the maths. So you could certainly go up and harvest some, then that would be a superb idea. And so this, is on the books. 2019, a project was created to try and actually do this and collect some antimatter. And it would make an absolutely astonishing fuel for a rocket. So if you could collect the fuel in orbit from the Van Allen belts, store it somehow in magnetic containment tanks, and then use it to drive your spacecraft, so you could fly very rapidly around the solar system and even potentially use it to create an interstellar probe. And there are a couple of antimatter catalyzed nuclear fusion engines where they would use the antimatter to kickstart a nuclear fusion drive that could fly probes out to the outer planets or even off to Barnard's star or Alpha Centauri, which would be absolutely fascinating if that ever came to pass. And if we're worried about our Van Allen belts, well, we could always go to Jupiter, because we think that Jupiter has enormous Van Allen belts as well. And if these were able to be harvested, and we could collect the antiprotons from there, then there might be a very, very rich source of rocket fuel indeed. But other than using it as rocket fuel, there have been some, what I think are slightly crackpot suggestions of making more room for satellites by draining away the Van Allen belts of the Earth. Not quite sure how you would drain the particles away, getting them away from the magnetic traps that they're in, or what you do with them afterwards. But if you were able to do this, you could make more space in that middle region where you could put yet more satellites. And if you did that for Jupiter, if you drained Jupiter's absolutely enormous Van Allen belts away, then you could actually avoid one of the problems of the surface of Jupiter's moons. So Io and Europa particularly are very, very much fried on their surface by high energy radiation as a result of the belts of material around Jupiter. And so the surface would be a very, very hostile place indeed. But as it says at the bottom, draining the Van Allen belts, what could possibly go wrong? Thanks very much for listening, and I'll see you on the next one.